Hello, my name is Jonathan Bisnet, and this is the first video in a series I'm going to do on op-amps, comparators, oscillators, and triggers. And in this video we're going to look at an inverting amplifier. Relatively simple circuit in this case with negative feedback. Being an op-amp, it needs negative feedback. So to calculate the gain on this amplifier, we need to look here at this formula here. This is how you would basically calculate the gain. The negative is due to the fact that it's going to invert the output 180 degrees out of phase, and then the voltage in times RF over RI, RF being the feedback resistor, RI being the input resistor. So whatever you put in is going to be multiplied in that fashion. So as an example here, if I put 1 volt in, I'm going to multiply that times 22K, which is my feedback resistor, over 10K, which is my input resistor, and I'll get negative 2.2 volts out. So in this circuit right here, currently what I have is a battery applying that 1 volt to the input. And if we look at the oscilloscope up here, what you'll see is that if I look at channel 2, which is my input, we're looking at about 1.04 volts. It's bouncing around a little bit. And channel 1, which is my output, is about negative 2.24 volts. Again, it's bouncing around a little bit, but very close. And some of this, they're not precise, but some of that has to do with offsets and the tolerance of the resistors, etc. But let's put it this way, it's pretty close. The other thing I have here is I also have a resistor. So you'll see this is my feedback resistor here, and this is my input resistor right here. I also have a resistor here on my non-inverting input. In this case it's 6.8K, and the reason that's there is for stability. It kind of helps the op-amp maintain a certain stability. And the way that resistor is calculated is to take the input and the feedback resistors in parallel. So basically if I take 10K times 22K, that product over 10K plus 22K, the result is 6.875K, so I used 6.8K to get me that additional stability. So anyway, now if I go in and look at the circuit I have built here, you'll see it here on this diagram. What you'll see is that I have 1 volt here as my input coming off of ground and going through my input resistor. Now the rules of an op-amp basically say no current flows into or out of the inputs of an op-amp. Now that's for ideal purposes, that's true, although some minor amount does flow depending on the quality of the op-amp, but it's generally negligible and for the sake of calculations can be ignored. So since our non-inverting input is at ground, and because no current flows into or out of the op-amp, that 6K ohm, 6.8K ohm resistor doesn't really do anything other than, as I mentioned, stability. The non-inverting input is at 0 volts. One of the other rules of an op-amp is that the two inputs will be at the same potential. So since I have 0 volts at the non-inverting input, I also have to have 0 volts at the inverting input. So that allows me to look then and calculate the current flowing through the 10K ohm resistor. If I take 1 volt minus 0 volts divided by 10K ohms, which I've done down here, I'll see 1 volt minus 0 volts divided by 10k ohms. I should have about 100 microamps flowing. Well, I have a meter hooked up, and it's showing about 95 microamps. So again, fairly close to what we expect to be flowing, but that's what's flowing across that input resistor. Now, since the input resistor, since the current flowing through that cannot go into the op-amp, it has to go up and around through the feedback resistor. So as you can see here, we're talking about 100 microamps flowing through that 22k ohm resistor, starting at a potential of 0 volts. So if I come back down here and look at that, I say 0 volts minus, in this case my voltage drop, 100 microamps times 22k ohms, and I'm going to get negative 2.2 volts, which again is actually pretty close to what we're getting out of this circuit. And if I look at the current flowing through that upper resistor, you'll notice it's about 99 microamps. So again, fairly close. Some of this comes down to the accuracy of my equipment and how close it can get to these small amounts. But about 99 microamps. So that's how you'd get to that negative 2.2 volts on the output. And as you'll notice, that's pretty much what we expected based on our calculations. So now, let me change this to 2 volts input. So now that I've changed the input to 2 volts, which you'll see there, we have 2 volts on channel 2 coming in. You'll notice my output is negative 4.4 volts, which again would be 2.2 times the input. So if we go down here and look at the formula for that, we're looking at 2 volts into the 0 volt virtual ground over 10K. We should see about 200 microamps flowing. And if I go look at the meter, we'll see that, yeah, we're pretty close, 198 microamps. And then from there, if we look at 0 volts minus the 200 microamps times the 22k ohm resistor, we should see negative 4.4 volts, which is what we did see. And through that upper resistor, you'll see that we have about 205 microamps flowing. So pretty close to what we would expect to see. And if you look at the basic calculation, you'll see that, if we put in negative 2 volts times 22k over 10k, we're getting negative 4.4. So once again, that's exactly what we expected to see out of this. So that's the circuit, and it behaves just about the way I would expect it to behave. I hope this helps, and thank you for watching.